Hello everyone, my name is Lara, and I will talk a little about our paper, Experimental and Numerical Study of 3D printed parts for pulmonary ventilator circuit. Well, the work was done by me, Daniel, Julia, Mateus, Olexiy, and we are from the University of Brazil. The presentation was divided into 4 parts: introduction, methodology, results, and conclusions. The context that generated this theme was the coronavirus pandemic at the end of 2019, where due to this disease, the most severe cases need to be intubated, and as there was a high demand worldwide, so we come across the necessity of facilitate the authorities' access to the necessary equipment to the pulmonary respirators. One way that was founded was the possibility of implementing 3D printed connections as a low-cost solution. But before implementing this innovation, we need the analysis of the efficiency of applicability by mechanical testing and numerical simulation of the flow. For making this analysis, we needed to find a model patient, which was founded by selecting the characteristic of the most of the population that was in the ECU in 2020. Also, this work aims to verify the possibility of using a double ventilatory circuit to watch 2 persons. The methodology was divided into experimental and numerical part. The experimental study was regulated by ABNT ISO 5356 standard. And there are 4 types of tests to be performed: coupling with cones, leak tests, drop tests, and measurements of diameters. The tests were made with both samples, original and modified. Here in the right, you can see the benchtop apparatus for performing the tests. What concerns to the numerical study, here we have the computation domains of Y connectors for the flow simulation. Here we have the original and here the modified connector. The edge 1 remains to inlet of the inspiration phases, 3 the outlet, and 3 are the inlet of the expiration phases into the outlet of the expiration phases. The same for the modified. The connections 1 and 2 are also assembled to one flexible piping of 1 meter length. The boundary conditions for the numerical study was the data of the model patient that was used as input on the didactical mechanical ventilator simulator. The model patient, or the 61 years old male patient with 168 centimeters and 73 kilograms. Where for the given patient, the data used were 390 millimeters of volume, 12 breathings per minute with 0.5 seconds respiratory pause, and 40 liters per minute flow rate. The flow graph showed the data to be used as input in the numerical simulation, that is, the velocity. The graph had to be adapted because the velocity gradient should be compatible with the method of solution, and this way, these curves should be as smooth as possible. Here, the curve adapted. Here, the point A represents the beginning of the inspiration, C, the end, D, E, F, the expiration cycle. The authors constructed the mesh on 1/2 of the connector due to its transversal symmetry. Also, you can see that the geometry is more detailed in the central part of the connector, because that is our focus place. Validating the mesh, we need to we made an analysis of state flow using a constant velocity inlet of 3 meters per second. The goal was analyze the behavior of the boundary layer, and the research was performed on the 1 meter long tube connected to both of the connector opening. In the simulation representing the respiratory cycle, the boundary conditions was the data obtained for the simulator and consisted of 2 steps, inspiration and aspiration. Where the study about the efficiency of both connectors was made calculating the total pressure drop in each one during the entire breathing cycle. The results of the research showed that there is a possibility of using the same mechanical ventilator on 2 patients simultaneously. The pre-ABNT 800 respirator has the maximum flow of oxygen pump of 200 liters per minute. In the severe case of the disease, the maximum use required per person is 40 liters per minute. However, there are some protocols to be followed, which is the patients must be in similar respiratory clinical conditions. What concerns to experimental results, the samples were placed in the oven in the humid environment and then installed on the test stand and connected to the moment and force measurement equipment. We observed that shape changes are possible with slight force application, and the 3D printed sample did better than modified ones. The mesh validation showed that the turbulent boundary layer occupies near 20% of the flow area, and the results of it, the no sleeping condition, validation the mesh. Here in the graph, we can see that near the tube wall, the velocity is about 0, and having a more significant velocity gradient here on the tube wall. The modified part presented minor stagnation pressure losses, as you can see here in the graph, and the total pressure loss of 61% less than the original part was calculated. The original part has a geometry that constrains the flow, which causes a high magnitude velocity in the transition region, which causes a high energy losses. The modified part has a smooth flow, what implies in the smaller velocity in the transition region and causes low energy losses. The original part has a higher number of vortices for the expiration process and a lower velocity flow at the end. The modified part has a faster and smooth flow, so we can conclude that the modified component is more efficient on flow transportation of both phases of the respiratory cycle. The conclusions of our work are that the experimental tests show that all connectors are within the norms. With the boundary layer analysis, it was possible to observe the present and influence, validating the computational mesh. In terms of the efficiency analysis, the 3D printed connectors are 61% more efficient than modified parts. And from a aerodynamic point of view, using a 3D printed part in the sharing mechanical ventilators speeds up the recovery of COVID-19 patients. On the other hand, it is essential that other tests have been completed successfully. I appreciate for your attention, and I am available for any doubts.